You guys ready? Okay, here you go. Okay, pre-announcement of the day. Here you go.
Thank you. Hi, I'm Spring.
And I'm Sakat.
We're from Alpha Kappa Psi, and we just wanted to remind you guys that today we're hosting an event on blockchain. It's called Disrupt and Decentralize. It's at 7 p.m. today at International House at Chevron Auditorium, and we're expecting to have a lot of renowned speakers from really important companies such as Coinbase, Ripple, IBM, Ambasave, CoinRoutes, and Oracle. We really hope that you guys will come out and show your interest. We know blockchain is in a really important concept that everyone's interested in right now.
We have free pizza.
Yeah, that too. Free food. Let us know if you have any other questions, and we'll be passing out flyers. Thank you.
Thank you. You guys are looking sharp. Okay. All right. Let's see. Announcements. The heck? So the exam solution exists. Not sure why it's not posted, but will be posted soon. Exam was really hard, but that's how exams go. All right. More later. Okay. All right. Moving on. Yeah. Who here also took the 61C midterm? Anybody? How was that? That's back to back. Were you just totally annihilated when you were done, or what? Yeah. Anybody else take a different midterm yesterday that wasn't 61B or C? 70 was Monday. Well, you had a whole night to sleep, so. Yeah. All right. You're welcome. All right. Hey, I put on the sheet before this. I got the midterm times done in November. So anybody who came later, that's their deal. Blame them. All right. So graphs. All right. This is going to be one of our last data structures of the semester. We're talking a lot about algorithms after spring break, and also we're going to talk a lot about algorithms on this data structure because they're very rich. So graphs are, in a sense, they're a generalization of linked lists and trees, and we'll see that they allow us to do all kinds of things. So specifically, the definition of a graph is the set of nodes, which are sometimes called vertices. Those both terms are used interchangeably, and they're connected pairwise by edges. So for example, this right here is a graph where this node is connected to its 5 neighbors. We can zoom in on them. So it's got 5 neighbors connected to all those. So a linked list is like a graph. I mean, it is a graph. It's just a graph where you have a left and a right. And a tree is a graph. It's just that a tree you have children and maybe a parent. So graphs are a generalization of that concept where you can go in any direction. There's no left, there's no right, there's no up, there's no down. You just have neighbors. Okay. Now graphs, there are a bunch of different types of graphs. You can have what are called directed graphs, where each connection has a direction to it. So you might imagine using this to model one-way streets. So you can go from A to B, but you can't go the other way down that street, so to speak. And there's also the undirected version of a graph where there's no notion of directionality. And they're both useful for different types of modeling problems. We can have cycles in our graphs, or we might not. So a cyclic graph, in the directed case, it means that there's some way to get back to where you started if you leave. And with an undirected graph, a cycle is it's whenever you have 2 ways to get from some place to another, basically. If there's a way to get back to yourself without backtracking. So if I go A, B, D, C, back to A. That's an example of a cycle. This graph is considered acyclic because it has no cycles in it. And same deal over here. And there's another feature of a graph you can add, which is labels, where you can decide to label edges. You can also label nodes. But here I'm showing only edge labels where I say that A and B, there's this weight or this value of 1. And this might be useful, for example, for imagining trying to model the cost to run wires from point to point. So maybe you have 5 houses you need to wire up, and these are the cost in wiring to connect them all up. Okay, that's just graphs in general. Now, I've alluded to some of this terminology, but I guess I'll go through even more because that's what we do when we get started with a new topic. So a graph, as I said, it's a set of vertices and nodes, and then those connections are called edges. And each edge you could think of, if you want, as just a pair of vertices. So if this is vertex A and this is vertex B, you can think of this edge as A-B or something like that, or a tuple that contains A and B. Now, if we say that 2 vertices are connected by an edge, we will Oh, yeah. So we have two vertices that are next to each other that have a connection. Those are adjacent. And optionally, as I've alluded, we can have labels or weights. Okay. Now, there's some other handy notions that are emergent from these definitions. There's the idea of a path. And that's just any sequence of vertices that's connected by a set of edges. So some example paths from the optional textbook. This is a path of length 4. Here to here to here to here to here. That's a path. And we can also have cycles. So a cycle is just a path. Intimidating crowd over here, just strolling in. Muscle in, find your space. Okay. So a cycle is a path whose first and last vertices are the same. So this is a cycle and is also a path. Just happens to be also a cycle. And so any graph that contains at least one cycle is considered cyclic. And we'll say that two vertices are connected if there exists some path between them. So if we look at this is all one big bunch of vertices, all of which are connected because there's some way to get from any of these to any of these others. And that's sometimes called a connected component. And in this case, this graph, it has 3 connected components. And if we say that all vertices in a graph are connected, then we say the graph is connected. And we use that term in the weighted quick union problem on the midterm. All right, any questions about terminology? Yeah. So can you have 2 edges connecting the same 2 nodes? There is a generalization of the concept we've used so far in class where graphs are allowed to have multiple edges. Our graphs will never have those, but sometimes in some other settings that's done. Yeah. So I didn't actually put this one over here, but the degree of a vertex is the number of edges that touch that graph, or that vertex. And we'll talk about that shortly. So this is 3 because it has 3 edges. Good eye. Yeah. So if you have a graph where the edges are directed, it still seems like there's some places you can't get to. So imagine that there's one node in the middle that just radiates outwards. In that sense, you'd still say the graph is connected. It's just not that everything is reachable from every other place. So if you just have one vertex in the middle and a ring around it, and the one in the middle just points outwards, you'd say it's connected, but not every vertex is reachable from every vertex. Okay. All right. So graphs are an incredibly useful tool for modeling the world. I mean, you already have implicitly done so all over the place. Like in some sense, the percolation problem, you could think of it as a graph problem in a way, where you're adding connections, but we did it in a more, a cleaner way. But there are a lot of other ways that graphs are useful, and we'll go through a bunch in a minute. But I'll give you some example just from the math side. Let's ignore applications for a minute. Let's just think about mathematically what could you do with a graph. That's interesting. So there's a problem known as the source-target-path problem, which is given a graph and 2 vertices S and T, is there some path between the 2? And so there exists some algorithm given a graph to try and solve this. And in fact, this is basically the percolation problem. Given a bunch of connections, is the source and the target, are they connected? Okay? So you've done that one before with disjoint sets. There's the shortest ST path problem, which is what is the shortest path between vertices S and T? So question for you guys. When you were doing the percolation homework, with your disjoint sets object, could you solve shortest ST paths? In other words, figure out what the shortest path is down versus going that way? Not necessarily. I mean, it sounds like it'd be tricky to do, because if you only have the weighted quick union object, you don't know with just the weighted quick union object, you definitely can't do it, because maybe your path, you have 2 choices, one that kind of snakes along and goes to the bottom, one that's straight down, but your code, because of the way you were storing your information about the world, you weren't able to do shortest ST path. With graphs, you can. And we'll talk about ways to do this in a bit. Cycle, does the graph contain cycles? The Euler Tor, is there a cycle in the graph that uses every single edge exactly one time? We talked about that during lecture 1. There's the Hamilton Tor, which is there a cycle that uses every vertex exactly once? So it's closely related. There's connectivity. Is the graph connected? That is there some path between all vertex pairs? It depends on how you define connectivity. So on an undirected graph, this definition is very clear. Biconnectivity. It's kind of a little more obscure, but is there some graph where in the graph, is there a vertex that you pull it out and the graph is no longer connected? So it's kind of a critical junction point, a bridge. So you can imagine this is useful if you want to, destroy the railways in some country so that they can't ship goods. Now you know the place to destroy, right? Maybe that's useful to you. Planarity. This one's kind of interesting. There are some graphs that if you try to draw them on paper, you can draw them so that no lines with your pencil have to hop over other lines. So some graphs can be drawn on a sheet of paper with no overlapping lines, and some of them you need more than 2 dimensions. Isomorphism, are 2 graphs isomorphic? That is, are they really the same 2 graphs? It's just, you just got to move the vertices around a little to show the same shape. And what's really interesting to me about graphs and why it's such a rich area of research and why many people have won Turing Awards just for their work on graphs is that when you look at this list of problems, it's not clear which of these problems are easy, that is any 61B student could just do them, no problem. They're hard, maybe it's the very last problem on the final and it's just brutally difficult, or it's computationally intractable where nobody knows a good algorithm. And, I won't talk about which ones are hard or easy here, but graphs are fun in this way, that you just make up some silly problem, and then sometimes the math behind it is really, really rich. And so what the next several lectures are going to be is trying to draw out what the techniques are for solving all of these graph problems, because solutions to graph problems have certain things in common. Okay? So I'll give you an example of a few examples of graphs that are useful. This graph I showed earlier was in fact a subway map of Paris, perhaps slightly out of date. And if you look at the subway map of Paris, we'll notice it is undirected. Right? So if you go in one direction, you can go back. If you get off the train, you can get off and go the other way. It is connected in the sense that any station can be reached from every other. And that's not true of every subway system. Sometimes you have to get out to go to other stations. Or they're not even on the same map. So there's a lot of cities where you have 2 competing subway systems that don't necessarily connect to each other. It is cyclic in the sense that there are ways that you could just ride in a circle all day, if you want. And it is vertex labeled. And here the vertices are labeled by color, and what the color means exactly, who can say? All right. So that's a graph. How about BART? So BART is a graph. Now here's a question for you. Is it also a tree? So I'll give you a hint, which is a tree is a graph with no cycles in it. Are there any cycles here? Yeah, there's kind of a cycle. It's a little tricky. It's actually a trick question. Depends on how you define it. So you could technically go San Bruno to SFO to Millbrae, but some of those edges don't exist at the same time of day. So it depends on which edges exist at any given moment. All right. Yeah. Now, this BART map, this is 2014. I got to add some more stations here. But anybody been to the new station? Wow. Why are you guys all going to that station? You from there or something? Oh, you live there. In the station. Nice. Sounds nice. How about, what's someone else? How'd you go there? Why were you there? Wow. My goodness. Some locals up in this piece. All right. Next up. So this is a very old graph of Facebook. This is 2010 when there was only tens of millions of people on Facebook or whatever. In this case, a visualization was produced where each node is a city and the weights are the number of friends between cities. And the goal here was to visualize in the world which cities had connectivity. Actually what's fun here is you can even just looking at the glowing edges, you can see some things that are missing. Anybody notice anything missing on this map? That seems like there maybe are people there? China seems pretty low on humans. Which is not, as I understand it, how it works, but I don't know. The Himalayas block the signals or something. I don't know what's going on. All right. I was in the airport in Shanghai one time, and I really needed to send a file. And I was like, wait, I can't use Gmail? And then I was angry, but I couldn't do anything about it. So anyway, if you guys are from China and you go back, I encourage you to, have a chat with whoever's in charge and tell them to turn Gmail on. All right, thank you. All right, next up, scientific journals. I like this one a lot. Too bad you can't see it, but you can look at it later. But I'll tell you how this one works. So this graph was generated from data and in a smart and interesting way. They somehow were able to take all these scientific journals and click-through data. So you're reading a paper on internet censorship, and then you click on a link that takes you to a paper in some journal, and then you click on a link and it takes you to something about, history of internet censorship. And what the clicks were tracking is which journals were linking to which. And they collected this number and they said, okay, people who are reading, let's say, this chemical engineering journal, they had 5,000 clicks, let's say, which was above a threshold to some other chemical engineering journal, so we'll draw a link. So a link means enough people above some arbitrary threshold are clicking from journal to journal. And so what they did with this is they used a graph layout algorithm. because that's another interesting problem, which is given a graph, how do you display it nicely? So this graph layout algorithm, it basically recapitulates a taxonomy of human knowledge and study. So in here we have sort of these biological sciences, there's genetics, environmental science, and so forth. And you can trace it all the way up here that plant biology journals, we'll talk about microbiology journals, we'll link to them, which goes to biochemistry, to analytical chemistry, to organic chemistry, physical chemistry, statistical physics, and then we arc our way up into mineralogy. Then you can come back down to economics, and then here you get to this giant web of other humanity studies. So I think that's a pretty cool graph. It gives you some intuition for how people think. Okay. Another one is the WordNet data set. This was alluded to during our hypernyms lecture. And this is a taxonomy of English nouns where we say, or basically English nouns, which is, this graph tells you that jumping is a type of descent. And descent is a type of movement. And movement is a type of change, and change is a type of action. And action is a type of human activity, which is a type of event, and so forth. So this graph is handy if you want to start analyzing language. And you could do all kinds of interesting problems with this data set, which is, by the way, a graph. All right. Any questions about graphs? Hopefully I convinced, yes?
So why does this picture look awfully like a tree, and how can it not be described by a tree?
So this is this a tree? This particular one is a tree. Is all of WordNet? Oh wait, this has two parents though. It's not quite a tree. It's close. Because group action is both a human activity and event. So not everybody has one parent. But it's close to a tree. Yeah. Yeah. So miracles. In this case, the reason the word miracle appears twice is these are two different usages in English of the word miracle. In the graph sense, these are two different nodes. It's just they have the same word associated with them. Each of these is actually not a word, but something called a syn set or synonym set. And this is a subtle difference. I don't know what it is. Yeah. All right. So let's talk about graph representations. We have the idea of what they are abstractly. And so I'm going to do one little trick first, kind of like what we did with weighted quick union, where I'm going to say, we're not going to call graphs by their name, like Miracle or Dallas, but we're going to give them each a number. And that's just going to make it so we have a canonical, clean representation. So the common convention is we're going to number nodes, which are going to have nothing to do with however you might label them. And then we'll use that number throughout our implementation. And let's say you actually did want to say that Austin is connected to Dallas and Houston. Well, we'd say, 0 is connected to 1 and 0 is connected to 2. And then I have a map from string to integer and perhaps also integer to string that allows me to look up who's who. Okay? So this is my intended graph, and we're going to use numbers instead. Now, because this isn't really an interesting problem, because we already know about maps, I'm only going to be talking about this part from here. But be aware, in real graph libraries, this is not such a surprising thing to see, that the graphs actually have vertex numbers, and then there's somewhere else that you write down what the numbers correspond to. When you do Project 3, you'll basically do that. Okay? So there's a graph API in the optional textbook that I'm borrowing for our class. And a graph in Java might look something like this. So we have public class graph or interface graph. Either way, we're not going to touch this real class. So there's a graph. In this case, it is a class because I have a constructor. So I say public graph int v, and that will create an empty graph that has v vertices. So the API for the graph we're going to present in lecture, there's a fixed number of vertices. There's no add vertex. This is not a general feature of graphs. That's just something we're going to do to keep life simple. Okay. So just like weighted quick union, when you make one, you get all your objects, and then you add connections later. We have an add edge method, which writes down connections, and it's kind of like union in a union find or a disjoint sets object. But the difference here is that we're actually going to track who's connected to who and not just what set they're part of. We have an adjacency method that you give it a vertex number and it gives you back an iterable of all of the vertices. And we use an iterable here just to drive home the fact that we don't really know how it's stored. Maybe it's a list, maybe it's a set, maybe who knows what it is. Maybe it's an array. So instead, we say iterable, and it's just up to Adj to give me an object that could be iterated over. And then we have a v, which gives me the number of vertices, and e, the number of edges. So that's what our graph API is going to look like. And so as an example of what you could do with this API, we could write a method that takes a graph and a vertex number. So 1 is Austin. And I want to know what cities are connected to Austin. How many cities are connected to Austin. That's what the degree method will do. And so what we'll do is we'll say the degree is 0, and then for every neighbor of Austin, we're going to add 1 to the degree. And we're not actually going to pay attention to what those neighbors are. So yeah, maybe W corresponds to Houston and another one's San Antonio, but whatever. Okay, we're just going to count them up, and then we return the degree. So in this graph here, the degree of the vertex 2 is 2, because it has 2 connected variables. Okay, so that's a sense of the API we're going to use. There are many other potential APIs out there, but this one's very simple, and it matches our optional textbook. Any questions about this? Yeah? Sorry, why is it 2 if what? So 2 is connected to 1 and 2 is connected to 3. Yeah, so 2, basically, when you say G add 2, you get back an iterable that you can call next on twice. The first time you call next, you get 1. The next time you call next, you get 3. All right, next, yeah. So is there a notion of balance? Not a natural one, because graphs are big, sprawling things that the structure is somehow really important. So I don't think there is so much a notion of balance. I mean, the closest thing I could think about is something called sparsity, which is the number of edges that any given vertex has. All right. Oh, yeah. So if, say, we add another connection to 1, so we do like 5, 6, and they connect it to 1, that's a great question. Let's add that now. Okay. So I like that example better. Actually, I'm going to do this. I should have had that before. Let's just do 1 vertex. So doing this, if we think about what the code looks like, it'll be the same. It's not some recursive function. So if this is we need to rename this vertex, say 4. Whatever, it's fine. It's a little ugly, but on the fly, slide creation. Oh, it's so ugly. Let's look at it. Oh, I was just sad looking at that. Okay. Anyway, this still has vertex 2. Good thinking. Yeah. So what's the ordering of the edges that come in? It's not specified in this API, though you can imagine that this iterable should return the edges in the order that they were added. But we don't have that specified here. Yeah. Though typically on exams, we will do that. We'll say, treat the edges as if they are iterated through in the order that the labels are alphabetical, let's say. You'll get that. All right. Okay, so how do you actually do this? How do you implement this graph? If I wanted to write some instance variables that let you implement the graph class, might they be? Well, the easiest and most intuitive way is called the adjacency matrix. And what I've got over here in green, these pictures here, is the logical graph, the thing in your brain. And then over on the left, I have the matrix that captures, like the variables in Java that capture this graph. So in the adjacency matrix representation, the idea is you make a 2-dimensional array of integers or of booleans, and you just put a true or a 1 value anywhere there's actually an edge. So in a directed graph, this interpretation, the way you read this table is you say, if the source is 0 and the target is 1, if the source is 0 and the target is 1, we see a 1, which means this edge exists. Okay? So if I give you this table, hopefully you can draw this graph from it. I'll give you another example. Okay, so we look at this row. So S is 1, T is 0. So is there an edge that goes from 1 to 0? No. And look, it's not there. Okay? If we change this to have an arrow there, this is the value we change. In an undirected graph, it's kind of a little funny. So the normal thing to do is that you do the exact same idea. It's just that you say that for this edge, this red one here, for example, the vertex V and the vertex W. Again, these are totally arbitrary letters. I could have put P and F here or whatever. So I just did V, W, S, T. So V is 1, W is 2, so we add a 1. But we also have a 1 from V2, W1. And what we get here is we get simplicity at the expense of a little space. We could do something a little trickier where the first row is length n, and the next one's length n minus 1, the next one's n minus 2, and the last one's n minus 3, and so forth. But I'm not going to do it. Okay? Just because this is really common. Yeah. So could you have a vertex with an edge to itself? This certainly allows it, right? If I put a 1 here, it does. Though the graphs we'll use in class typically won't, right? So what I would say is like 99% of the time in 61B, I'll say no self-edges and no multiple edges. But there are circumstances where it's useful in your model. Like, for example, suppose I want to capture the fact that there's two different ways of getting from the front of the room to the back, right? There's these two different pathways. I might consider this a graph with two edges that go from this vertex to that one. So it just depends on your problem. Yeah. So you could use Booleans, and it would save you some space. I just did ones because the optional textbook does. All right. So I got a question for you. Let's see if this all makes sense. Give you a chance to do some digesting. Here's a piece of code that prints out the entire graph. So, for example, it will print out 0, 1, 1, 0, 1, 2, 2, 1, 2, 3, 3, 2. So in this case, it'll print out 6 edges. So it prints out, you can think of this as it prints out all the edges of the graph. And let's imagine that we've implemented our graph as an adjacency matrix. Your job now, figure out what the runtime is. And I've given you 2 sub-questions that might be helpful for figuring this out. Give it a shot. Uh-oh. Okay. If you're looking very closely on your device, you may notice that the text doesn't match, but don't worry about it. We're going to dead heat between 3 answers. Okay, so this for each loop here, we do for int w in the adjacency list or whatever, or the adjacent of the neighbors of v, and we print things out. How long do you think this loop will take? Here. So think about this. We need to go through this list, right? So we say for int w, which is all of the vertices that are neighbors of v equals 1, how long do you think it would take to iterate through these? Any ideas? Yeah, v. So v is the number of vertices. So this, the runtime of the for each loop is v. How many times do we actually need to call the for each loop? V. So actually the answer in this case is v squared. So the runtime of each for each call is, to finish this whole loop, is v, and there are v calls. Okay? Graph runtimes are tricky. Probably a lot of you didn't get that. Yeah? So the argument was, shouldn't it be v squared plus e because of the fact that you're thinking about the edges? Well, I would counter by saying that e is basically the number of ones in here. So I don't think you really get anything more out of that. Like, e is definitely always going to be smaller than v squared. It's a smaller term. It's like n squared plus n. You just say it's n squared. V squared plus e, you just say it's v squared. Okay? Other thoughts? Okay, I got a harder one for you coming. Don't worry. All right. By the way, I just want to note real quick that when you ask, what does g.adjacent of 1 return, well, it gives you an iterator where the first time you call next, you get 0, and the next time you call next, you get 2, and then has next is false. So it's some object. Okay. All right. Okay. Another graph representation out there. This one we're not going to use, but I'll mention that it exists, which is rather than storing a 2-dimensional array of Booleans or 1s and 0s, we instead store a collection of all edges, and an edge will just be a pair of ints. So if we think about this is a set of tuples, let's say. In Python it would be. So we have 0, 1, 0, 2, and 1, 2, and the first value of the tuple tells you the source, and the second one tells you the target. And this also gives you a graph. Okay, you could do this. But we'll move on to a third approach, which is the one that's most common, which is called the adjacency list. So in this approach, what you do, it kind of feels a little like a hash table, where for every vertex, you're going to give a list of all of the neighbors. And the list will literally be like a list of numbers. So 0 has the neighbors 1 and 2, 1 has the neighbor 2, and 2 has no neighbors. And in this case, The neighbor is who you are pointing at, right? And this is, for most purposes, the most popular way to represent graphs. Sometimes it's better to do one of the others, but almost all the time, this is what you'll see. Okay? So here's a harder question for you, if the other one wasn't hard enough. And hopefully this yell key actually works, because I forgot to change the word shout. So let's say we're using this new approach. What do you think the runtime might be? And I have the same questions to get you thinking. I'm crossing my fingers. The yellkey.com/laugh works. Okay, it works. This one's kind of sneaky. Okay, I'm going to interrupt you, and then I'm going to do some thinking real quick. I'll give you a chance to think again. What do you think is the runtime of this for each this time? So when I do the for each, what does that mean I'm doing? I'm going through one of these lists. So what's the runtime to go through one of these lists? It's the degree of the vertex. It's how long the list is. So what's the minimum length this list might be? 0. And what's the maximum length it might be? v minus 1. So the runtime of the for each loop could be anywhere between 1 and v. And how many times does the for each loop get run? V. So what I'd say then is in the best case, the runtime is v, and the worst case is v squared, because the runtime of each of the for each is at best constant, and at worst v. Okay. I could also, by the way, have said theta 1 in the best case, theta v in the worst case, but I just did it the lazy way. All right. So this seems to me not one of the answers. Okay, well, it's still one of the answers. So I'm going to let you think about it again. So I've just told you what the answer is in terms of v, and I gave you a best case theta and a worst case theta. But you can also give a theta that works for everything, and I'll let you try and figure out which one it is. It took me a long time to understand this concept, by the way. So if you leave lecture feeling shaky on this is okay. I'm going to wait another 15 seconds. Like you guys are murmuring to each other. Okay. Not a lot of bold answers on this one. All right. Okay. Turns out the correct answer is v plus e, and let me walk you through why. Okay. Now, let me tell you, graph runtimes that involve two variables are surprisingly tricky to understand, and even having taught this class a lot, I occasionally slip up. So it just because you have to be pretty careful about it. So it turns out that there are two answers that are reasonable. You could say the best case runtime is theta v and the worst case is theta v squared. Or you could say that, well, it just period, the runtime is theta v plus e, and here's why. Okay. So the way to interpret this is, remember that asymptotics always involve v and e are, in this case, are always increasing. Okay. We're not saying how they're increasing, but they're both increasing, and they could be increasing in a different rate than each other. Okay. So what we'll say is that no matter what the shape, and by here shape I mean like the category of graph, no matter what shape of graph we're building as v and e grow, I'm gonna show you here that the runtime is always theta v plus e. Okay, so as an example, let's imagine that because the whole point of asymptotics is that over the course of time, my data structure is getting bigger, and I want to show that as my data structure gets bigger, that my runtime grows in a certain way. So one example is, let's imagine we have a special type of graph. This is just arbitrary, where every vertex is connected to its square. So 2 is connected to 4, 3 is connected to 9, 4 is connected to 16, 5 is connected to 25, all the way up to the big V's. So in this case, the number of edges is going to be really small, right? It's going to be the square root of V. So the graph is very sparse. Most vertices don't even have edges, and those that do don't have many. Okay? Well, I guess like let's say there's only up to 25. In that case, vertex 6, 7, 8, and so forth, they have no edges. Okay? So the number of edges is square root of V, and so just plugging in square root of V into this equation I said is right. We say V plus square root of V is the overall runtime. V grows faster than square root V, so the overall runtime is just V. Okay? That's the best case. A worst case example graph would be that the E grows really quickly. Every vertex is connected to every other. So if every vertex is connected to every other, how many edges are there, roughly? V squared-ish. So in that case, we'd say the number of edges is theta V squared. So the overall runtime is V plus V squared, which is just V squared. So what I've shown you here is just a couple of examples that this is the extreme case where V grows really slowly compared to E. And this is this is where E grows really slowly compared to V, and this is V grows really slowly compared to E, and we end up getting back those same best and worst cases from before. So hopefully I convinced you of this. And the V plus E is a little trickier, and this is just showing you that V plus E is sort of a tricky way of writing best case V, worst case V squared. And this is a subtle set of arguments, and it relies on some deep thought. All right, any questions about it? I'll try and do my best, but I'm not going to sit too long on it. Yeah. Yeah, so what is V? Well, maybe I should have said this very clearly. So V, okay, in case it was missed, because I don't think I actually said it out loud, V is total number of vertices, and maybe something that's really important is that E is the total number of vertices in the is the total number of edges in the entire graph. Okay, and so I feel a little bad for not actually making that really explicit, because some of you may have been listening to this with a mental model that E was like the average number of edges for each vertex, or like the number of edges for a specific vertex, but it's the total number of edges in the entire graph. Okay? Yeah, one quick question. Yep. Yeah, I guess multiple, that's not usually what multiple variables for, is for eliminating cases. It just happens to work here. Yeah, real quick. So if everything is connected, E is V squared, because 0 is connected to 1, 0 is connected to 2, 0 is connected to 3, 0 is connected to 4. If you think about it as the matrix, right? It's the matrix, every square in it is filled in blue, except for the diagonal. So it's two triangles, so it'll be squared. So you can think about and I'm sorry if you didn't totally get it. I mean, this is a hard concept, right? And this is a new way of presenting it, so hopefully it worked today. So these are the runtime of some basic operations for each of the different representations. There was the adjacency matrix and the adjacency list. And we talked about, for example, how iterating through is time V for a matrix, and it's constant time. Nope. Okay. See, I changed something from before. So theta 1 up to theta V. Sorry, I changed the table right before class. Don't do that. Except I like this table better. Okay. All right, there we go. Anyway, so you could compile such a table and think about other different operations that might pop up. Okay. Print graph is the one we did in class just now. This is V squared and V plus E. You can think about other potential questions you might ask about a graph that are basic operations. Okay. There's also how much space they use, which we won't talk about here. So to summarize this, the important point here is not every little thing on this table, though it does give you some B-level study guide problems to work on. But in practice, adjacency lists are how people usually represent graphs. And graph algorithms, as we'll see, they rely really heavily on this construct, the idea of going through your adjacency list in this case. Okay. I'll also note that most graphs are generally fairly sparse in the sense that V squared edges is not particularly common in a lot of applications. If you think about like a map of roads, there's not usually a road from your house directly to like New York City. Okay. All right. What might this look like as a piece of code? Well, here's the graph class. We have a number of vertices, which is final, can't change. And then we have a list of integers, which is the adjacency lists. When you create a graph, you get a bunch of empty adjacency lists. When you add an edge, you make a call. This is for an undirected graph that adds each vertex to the opposite vertex's adjacency list. There's no particular order. And then the iterable, it just returns adjv because in Java, the list interface implements iterable. Okay. All right. So now let's talk about a little bit more. So actually, I want to say one more thing about this. This, again, I have to repeat that this is a pretty tricky concept. It'll take you some time. Might have to sleep on it a few nights, but it's a good one. All right. So now let's talk about what you can do with graphs, real problems you can solve, and focus a little less on the mathy runtime thing. All right, so I got a problem for you to think about, which is, suppose we have a graph, undirected, and we want to know, does there exist a path from vertex, say, s equals 0 to vertex t equals 7? Here's an example you can use to think about it. So an algorithm I might suggest is, well, my recursive algorithm is s equal to t? If so, return true. Otherwise, we'll just check all of s's children for connectivity to t. Okay? What will go wrong here? So, for example, the connected 0, 7 call, it says, does 0 equal 7? No. So if connected 1, 7, return 2, return false. Why will this approach fail? Give yourself 40 seconds to figure out what I'm talking about, and then try and come up with an answer. And I guess children, I really should have said neighbors. It's not a tree. Okay, what do you think? Anybody spot any potential issues? Yeah. Let's see. Well, but still, you should eventually, if there is a connection, it won't short circuit early. Yeah. You could have an infinite recursion. That's the actual issue. So if you get to 1, it's possible that when you iterate through 1's adjacency list, you get to 0. So you end up in an infinite loop. So how do you fix this? Anybody want to suggest an idea? Yeah. Yeah, you record where you've been. Leave some breadcrumbs. Okay? So this is an idea. This recursive connectivity, we'll call it for the moment. Let's see. Did it actually work? Okay. So how this is going to work is we're going to do basically what we just stated, recursive search of our graph, but we're going to mark each vertex as we search. So the way the algorithm is changed is when we check connected, the first thing we do is mark S, and then we'll only check unmarked neighbors. So when we start at S, we'll say, is 0 equal to 7? No. Okay, actually the first thing we did was mark it, which was turning it white. And then we say, is 0 equal to 7? No. And then we say, is it marked? Sorry, got ahead of myself. What are 0's neighbors? 1. Okay, so we check 1, and we say, is 1 marked? No. So then we'll go there, and we make a recursive call. Okay, is 1 equal to 7? No. Okay, then we have to consider all of its neighbors, and we say, is 0 marked? Yeah, it's already pale. We've sucked all the juice out of it, so we're not going to go back. So then we go, okay, how about 2? Well, 2 is a good place to go. And notice we're not checking 4 yet. That happens later. Like if we explore all of 2 and we're done, then we'll come back to 4. Okay, so we'll go straight to 2, and we check to see if 2 is connected to 7. Okay, we mark 2. We say, is 2 7? No. Is 1 marked? Or sorry, what are 2's children? 1 and 5. Is 1 marked? Yes, so don't go that way. Okay, go to 5. Okay, 5 has 3 children. Let's assume that we just happen to check in numerical order. So we'll go to 4. Now, it is true that this is also 1's child or neighbor or whatever you want to call it. But that's okay. We found a different way to get there, whatever. So we get to 4. Is 4 7? No. Okay, so what do you suppose we should do next? Check 3. We go to 3. No more children, so we return false. When we return, we end up here. And if there was nothing else to do, we would return false. Is there anything else to do? No, we return false. Okay, now we're back to 5. Is there something else to do? Okay, so then we're not going to return false yet. Okay, even though our buddies said false, we're not ready to say that ourselves. So we'll check 6. We check 7. And in this case, we're going to return true. So once you return true, we're going to pass that true back up the chain. And so eventually we get to the top. Okay, so that's our recursive connectivity problem, or idea. So it just takes a little extra space, and it takes an algorithm that is bad and gets stuck in infinite loops, and now it works. Okay. So this recursive, actually, any questions about this process I should have asked? All right. Oh, yeah. Well, I mean, it's a recursive algorithm, so you're going to have the recursive call anyway. So the fact that you have to climb up the chain, that's just the nature of recursion. The nice thing is, well, no, that's just something we're going to have to incur. We accept the overhead. All right. So this idea is, as it happens, known as depth-first traversal, and is also known as depth-first search, as we'll see in a second. And the basic idea of depth-first traversal of a graph, simply similar to what we saw with trees last week, is that we're going to go deep before we go wide. So if we visit, let's say we get to 1. We're going to visit all of 1's children before we visit any of 3's children. Okay? That's just what we mean by depth-first traversal. We go deep into the tree. Now, I'm not usually somebody to put comics from the internet in lectures because it's just not my style to be referential. But I still think this is a nice visceral way of understanding depth-first search. So this is the next KCD comic in which the character is preparing for a date and says, what situations might I prepare for my date? So medical emergency, dancing, food too expensive. Okay, what kind of emergencies can happen? Snake bite, lightning strike, fall from chair. Which snakes are dangerous? Let's see. Corn snake, garter snake, copperhead. The research comparing snake venoms is scattered and inconsistent. I'll make a spreadsheet to organize it. And so by the time your date arrives, you're still wearing a towel, and when they say, I'm here to pick you up, you're not dressed, you reply, by lethal dose, the inland taipan has the deadliest venom of any snake. And so the idea here is that a depth-first search was the inappropriate way to prepare for your date. Okay? That's all. All right. So how would you actually implement this thing? Right? We know what depth-first search is. We understand its limitations. So there's a common design pattern in graph algorithms, which is rather than adding a depth-first search method to your graph class, we will instead build objects that are able to traverse graphs and record information. So what we're going to do is create a class called paths, and it's going to have a constructor where we give it a graph and a source vertex, and it's going to think about everything it needs to think about with this graph and say, okay, I'm going to gain enlightenment, understand everything about this graph. And then you can ask your Bodhisattva paths object, basically, does this vertex, let's say we give it the vertex 0, we can say, hey, paths object, you have studied this graph in detail. So tell me, is there a path from 5 to the source I told you about earlier? And she'll go, well, of course. You can also ask, what is the path to 5? And this paths object will say, oh, well, to get to 5, you'll go 0, 1, 2, 5. That's what path 2 will return. So this is a very common pattern, especially in graph processing, where you create the graph, and then you hand it to an expert that's able to process things about it, and then you query that client for information. And so here, where does all the actual work get done? Paths, the constructor. So the constructor does the work, and then the methods are just there to give you the information later. Okay? So for example, we would say paths P equals new paths G comma 0, and that might take some time because you have to crawl the whole graph. But upon studying and gaining information about this graph, you can then ask, is there a path to 3? Yes, here it is, right? You'll get true. And path to 3, you'll get an iterable, which is 0, 1, 4, 3, perhaps. Or maybe 0, 1, 2, 5, 4, 3, depending on what the paths object does. Okay? So how does this work in terms of implementation? Well, to visit a vertex, remember I said you have to mark the vertex and then recursively visit all unmarked vertices. In terms of the data structures that our paths object will have, one way we could do it is just have a Boolean array called marked. And then we can also track how to get places based on an edge2 array, where we might say edge2 of 4 equals 1 means the way to get to 4 is to use 1 to get there. So these two data structures allow you to do the magic process of pre-compiling or pre-processing this graph, and then you can get the answers back pretty conveniently. So let's get a sense. This is going to be almost the exact same thing, but now a little more Java-y, where we're going to record our marks explicitly in data structures that you would maybe have in a Java program, and specifically a Boolean array and an int array. So here, we are going to do, this is called depth-first paths, and since this is an instance of the depth-first search idea, I'm also going to just write out DFS instead of writing out depth-first paths everywhere. Okay? So DFSV, how it works is we start with all the vertices unmarked, and as we go, for each unmarked neighbor, we're going to set the edge2 value and then call the DFS method on its child. Okay? So we start with DFS 0. What we do is we mark 0 and say true, it has been marked. And then all of its children, we will set edge2 equal to 0. Okay? Now we keep moving and we get to 1. In that case, we mark 1, which means setting a Boolean to true. And then we say 2, its edge2 is 1. And we're only going to set that edge2 value of 2 based on We're not going to do it for all the neighbors. We're only going to do one at a time. Okay? So we repeat this process over and over. We get up to 4, let's say. And at this point, we've marked lots of the graph, but we're not done. And you can imagine, once we're at 4, we can actually trace back our steps. When I said we're leaving breadcrumbs, we're leaving them in the sense that I can say, okay, how did I get to 4? How did I get there? Here's 4. Well, you saw it. Okay, how did I get to 4? From 5. That's listed here. So the way I got to 4 was 5. The way I got to 5 was 2. The way I got to 2 was 1. The way I got to 1 was 0. And so we'll keep doing this over and over. And by the way, I happened to write down the order in which this method got called. So it happened to be this thing, which kind of feels like a tree traversal. And so I eventually get done with my whole algorithm. And the pre-processing, the thing that you get, like the result of your pre-processing, is this array that everything is marked. And this edge2 array has certain values in it. Okay? So I'll leave this as, this is obviously, and it's maybe a little more interesting to do on your own. So that demo is there for you to play with. Okay? Oops. All right. So question for you, to see if this made sense in our last minute. Okay, we barely have some time. How would we write has path to? So the paths object thinks carefully about the graph. How do we say has path to? What would it do? Here's its data structures where it recorded everything it learned. What do you think you'd do? Yeah? No? Yeah. Yeah, so if it's marked, you got there somehow. So you just literally return marked of 5 or whatever. So in that sense, marked as has path to will be really fast. Okay. So just to summarize what we did with that, and I'll let you out of here in a minute. Depth first search, it's guaranteed to reach every node that can be reached. It takes runtime v plus e, and we'll do the analysis next time. And the runtime can actually be a little faster if it quits early. Okay. So that's all you got for today. So Friday, perhaps I'll see you, perhaps I won't. If you're somewhere else, have fun in that place. Thank you, guys. Hi.
The thing with China, you said?
Yeah.
I told